Okay, so all right, welcome to the first co-com of the new semester. So this semester is going to be a little bit different. So I am the co-com chair, but I'm only half a chair because we're doing a lot of interesting talks next month with a lot of people who might be looking for jobs here. So those will be on Tuesday and Thursday, starting next week, going into February. So we encourage you all to come to those, get a lot of interaction between you all and the speakers coming up. But today is all about Ross. So Ross joins us from Geology Department. So Ross graduated the exact same year as me, had same amount of postdoc, and started the same day as me. We actually met during orientation, and he's here not because I know him well and I've had a beer with him. He was actually suggested by the department and went through all that process, but he has a lot of connections, despite being from geology, with astronomy because he's interested in planetary geology. So he primarily does two things, seismic imaging of the Earth, but also of Mars. And before I knew all of that about him, he's been over to my house, and when he comes over to my house, he talks about marsquakes. He's a real big enthusiast about that. Yeah, I'm gonna let him talk about his work and let him get into it. But here's Ross, and I wanted you to all know that he's he's an expert in this, and he has I don't know, I'm really impressed by him. So go ahead and get started.
They can't see your screen on Zoom.
They can't see my screen.
Yeah. It's like a black screen.
I think you might want to do the PowerPoint itself if you can.
How about now?
Yeah, now it's good.
Okay, perfect. All right, thanks so much, Kirk, for the introduction, and I'm really happy to be here. You know, this is actually sort of part two of yeah.
Sorry, could you hide floating video?
Technical issues.
Sorry for interrupting.
Not a problem. Yeah, I'm really happy to be here. And as Kirk mentioned, you know, I'm interested in a lot of planetary science. And I think it overlaps with some of what your interests are here. So, you know, if you want to talk more, I'm in the natural history building. Send me an email or stop by my office. So yeah, today I'm going to talk about Mars and what we've learned from the NASA InSight mission, which was the geophysical lander mission that took place between 2018 and 2022. My talk is titled "A Seismic View of Mars from Crust to Core," which kind of alludes to the idea that we're going to cover a lot of ground. And to kind of give you a bit of context or for what my goals are for this talk, I really, rather than it being kind of a traditional research talk where I'm focusing on really kind of like one or two studies and I'm going to go into a lot of detail, I'm going to cover a lot of ground and tell you about some of, at least in my opinion, the most exciting science that came out of InSight. And so that encompasses work that both I've been involved in through part of the InSight science team, which was a really big team, international group led by NASA, but also in collaboration with ESA and various academic institutions. And so some of this work is I'm involved in and some of it's not, but I want to give this kind of big picture of the InSight mission. All right. So my slide advancer is not working. But it's fine.
I need to click on the slide to get it in the foreground.
There we go.
Oh, maybe click that OK button to get out.
Does it work?
Yeah, I think it's good now.
Okay, cool.
No, it's not.
Click that button.
Okay. I'll just do it the old-fashioned way. All right. So let's first get acquainted with Mars or reacquainted with Mars, depending on your background. Here's Mars. It's showing its face with Valles Marineris, and here this is this big canyon system. You can see a couple of ancient volcanoes here associated with the Tharsis Rise. Olympus Mons is just out of view on the other side around here. And so, no, okay. And so just some basic facts about Mars. It's a little bit farther from the sun than the Earth. It's about 1.5 times as far. The radius is smaller, so it's a little over half the width of the Earth. The radius is about 3,300 kilometers. Compare that to about 6,300 kilometers for the Earth. It does have an atmosphere, but it's much thinner than the Earth. So at the surface of Mars, it's about 1% of the Earth's atmospheric pressure. The atmosphere is mostly carbon dioxide. And so even though it's sort of this faint, weak atmosphere, in the context of seismology, it's actually quite important because it turns out that the atmosphere can sort of contaminate the seismic signals we're looking at, and it's going to make it so it makes it so you need to be very careful with how you treat the data sometimes. There is a liquid iron core. I'll talk more about the core, but there's not an active geodynamo, so there's no active internally generated magnetic field, even though there is remnant magnetism that suggests there may have been a planetary dynamo in the past. So this is kind of an ongoing mystery. But we do know there's a liquid iron core, and I'll talk more about that. It's also a single plate planet, unlike the Earth, which has plate tectonics, where the lithosphere is fragmented up into these different plates that kind of move relative to one another and produce a lot of the seismic activity we see on this planet. It's in the regime we would call a stagnant lid. Okay, so it's basically a lithosphere that's largely unbroken. And so we'll talk about how you can generate seismic activity on this type of stagnant lid planet. And lastly, it very likely used to have liquid water on the surface. I think there's very few scientists that would argue with this. And in fact, you see evidence of it all over the surface in the geology. We see sedimentary deposits that were deposited underwater. You can see fluvial features all over the place. And we can actually potentially gain insight into the water in the subsurface looking at seismic data. All right, so that's one of the things I'm going to talk about. It's a little bit contentious. One of the questions, on that topic is, even if there used to be such a prominent hydrosphere, what happened to all the water? Was it all lost to space? Is there liquid water in the subsurface now? Is there a cryosphere? Or has the water been sort of incorporated in hydrous mineral phases? Just a kind of a quick picture of the main layers of the planet. If you kind of squint your eyes, it looks a lot like Earth in terms of the main layers that are there. Okay, so starting in the interior, we know there's an iron core. It likely is alloying with some lighter elements like oxygen and sulfur. There's a question mark here on the inner core because we're not sure, although there is a recent paper that has come out that argues, based on InSight data, that there is a solid inner core. But it's quite clear that there is a liquid iron core. Moving further out, there's a silicate mantle that comprises most of the volume of the planet. So this is a rocky mantle that is convecting sluggishly over geologic time. It's largely made of a rock called peridotite, which is similar to Earth's mantle. And then there's a thinner crust that's also rocky, so it's made of mostly silicate minerals. And we think it's about 50 kilometers thick. It's largely made of a rock type called basalt, which is a volcanic rock that makes up the Earth's oceanic crust and also the dark mare on the moon. So it's a very common type of volcanic rock in the solar system. All right, and then here's our thin atmosphere. Mars has long been a target of exploration. There's a lot of different missions that have gone to Mars, both orbiters and landers. Not all of these have been successful. All of these ones failed for various reasons, whether they exploded on takeoff or missed the planet or crash landed on Mars. You can see that there's a long history of kind of failed missions. So, keep this in mind when we're talking about sending people to Mars. Although that being said, over the last several decades, especially NASA has been very successful at getting stuff to Mars, successfully landing on the surface. All of these missions, well, besides Tianwen-1, the Chinese mission, there's a lot of successful NASA missions that have landed on the surface, including InSight, which is right here. They're not positioned where they actually landed on the surface. These are the ones that made it. Okay, so that brings us to InSight. This is InSight. It was designed by Lockheed Martin. This is the seismometer size, which was engineered by French scientists in collaboration with ESA. So a lot of the data I'm talking about is going to be coming from this. This is the seismometer on the surface. It's tethered to the lander, and so let's think about why this mission was selected and what we were trying to do. These are the mission goals as stated by the PIs of the project. The primary science goal was to understand the formation and evolution of Mars. That's kind of a tall order for one lander, but you guys can be the judge about how far we made progress on that. And so I'll talk about that more. And then second was to determine the level of tectonic activity on Mars. This one's a lot more straightforward, and hopefully I'll convince you that we have a much better understanding of the tectonic activity on Mars. I'm going to talk about both of these aspects of the mission, but I'm going to do it kind of backwards. So I'm going to start with talking about the tectonic activity on Mars and talking about what is causing marsquakes, the mechanisms behind the seismicity that we observed. And then I'm going to get into how we use those marsquakes to constrain the internal structure of the planet, and then what that tells us about the dynamics and sort of history of the planet. Okay. Real briefly, just if you're interested, these are some details of the mission. It was a Discovery class mission. It does have an acronym like everything NASA does. It was launched May 5th. This is right around the time I defended my PhD. And it was actually the first mission launched from Vandenberg in California. It arrived on Mars on November 26th in 2018, and it landed in a site called Elysium Planitia. So I'll talk more about that momentarily. And unfortunately, it is no longer operating. It exceeded the proposed lifetime of the mission, which was, I think, 2 years. It lasted more like 4 years. But unfortunately, last contact was December 2022. It lost power because of an accumulation of dust on the solar panels. Okay, so this is a picture of the topography of Mars. Red is high topography and blue is low. And it shows almost all of the NASA landers. You don't see Percy on here, but that's somewhere up here near Jezero crater. Here's InSight, and it's near the equator. This is the Elysium Planitia region. This is Elysium Mons. It's a volcano. And you can see it's this kind of interesting area between what we call the dichotomy boundary, which the dichotomy boundary separates the southern highlands, this red region of highly cratered terrain, and the northern lowlands. This is this younger volcanic plains that's not as highly cratered. All right, so here's the landing site. And it's actually, it'll come up later, but it landed near an area, a tectonic feature called the Cerberus Fossae, which is around here, which is an area of relatively recent volcanism. Yeah.
Why is the northern plane not cratered?
It's younger. The crater density is one of the primary ways we constrain the age of a surface. So there's some resurfacing that has taken place on Mars, where this is kind of this ancient crater terrain. The northern lowlands are volcanic plains that developed younger or later than the southern highlands. And you can see that in the fact that they're not as densely cratered. But all of the surface here, most of the features you see are very ancient. So everything, and what I mean by that is like 3 billion years or older, a lot of these features have developed, including like Olympus Mons and the development of the Tharsis Bulge here. So it's a very ancient surface, but the highlands are older, and we know that from the crater density. Yeah.
There's a question online from Brian.
Yeah,
Hi.
sorry. I know it's not the subject of your talk, but the deep blue little region, is that a crater?
Yes, that's an impact basin. Yeah.
Cool. Thank you.
Mm-hmm. Okay, so after it landed, InSight got down to business. It deployed its seismometer. This is size. It's tethered to the lander, and after a couple months, there was a shield deployed on top of the seismometer to protect it from the environmental conditions. So this is a wind and thermal shield. Was there a question in the back? Yeah.
Sorry, is it still active? Are the volcanoes still active?
So the volcano, as far as we know, no, the volcanoes are not active. Meaning like Olympus Mons and some of the Tharsis volcanoes. But I will talk. I'll get there. Okay, so there's evidence that there could be ongoing magmatic activity, but we have not observed volcanic eruptions. Okay, that's a good question. It's one of the things we're trying to understand with these types of data. Okay, so let's look at some of the data, and I'm going to start by showing a very complicated plot, but I will try to do my best to explain it. First of all, if we think kind of big picture in the mission, more than 1,000 marsquakes were detected, and that's what's kind of summarized in here. So this plot shows on the y-axis, it shows the sol or the solar day since landing. So this is early in the mission. This is 1,000 days after landing. A day on Mars is a little more than a day on Earth. It's 23.5 hours approximately. And then across here on the x-axis is the local Mars Standard Time at InSight. So each strip is showing the colors, the background colors. Each strip is showing for a day the acceleration power spectral density of the seismometer. So the dark purple is minus 200 decibels. That's 10 to the minus 10 meters per second squared. Very, very low acceleration of the ground. And then the other end of the scale, this yellow, is 140 decibels. That's sort of the louder periods of time. All right. And so if you can look at a single day and get a sense of the acceleration by kind of looking across and seeing how the color changes. One thing you can plot on this too is when the local sunrise and sunset happened. And so that's what these lines are showing. So sunrise, sunset, and what you notice is that in the daytime, the ground accelerations are much higher. So higher amplitude accelerations. That's because it's windy during the day at InSight. The wind is basically driving pressure changes that couple to the ground. And you can see that because there was a pressure sensor that was very correlated with the seismic data. Okay, so sort of co-modulate and tells us that the pressure changes are driving this noise that makes it loud during the day. You also see the seasonality. So this is spring, summer, autumn, winter. In winter, it's yellow or seismically loud pretty much all year round. So the winds are blowing all year round. Superimposed on this, all these scatter data, all the scatter points, those are the marsquakes. And so you can see when they were detected. And they're pretty much all detected during the quiet periods, as you might expect, particularly after sunset. So all these points, they correspond to different types of marsquakes and different quality marsquakes, which I'll get to soon. But these marsquakes were mostly detected kind of in the early evening and night. So we are kind of biased by the noise conditions in terms of when we were able to observe marsquakes. So marsquake detection is seasonal and also it follows this kind of diurnal cycle. So over 1,000 marsquakes were detected. We can break them up by different sort of characteristics. The main way we separate them into different families is by their frequency content. So the two main types are called the low frequency family, which are broadband and low frequency events, and then the high frequency family, which are these other events. This plot is showing a spectrogram of 8 hours of seismic data. So this again is time. This is frequency. The color again is acceleration power spectral density. And you can see basically that across this frequency band, you see different signals. And these brackets kind of are color coded to correspond with the frequency ranges of the different marsquakes. Okay, so broadband has energy between 10 seconds or 1/10 of a hertz up to 10 hertz. So kind of across the whole range. Low frequency events has energy below a hertz. This line is a hertz. So this is sort of an example of the low frequency event. High frequency has energy above a hertz. 2.4 hertz events are a special category that only really have energy kind of monochromatically at 2.4 hertz. It's likely an excitation of a local resonance. And then high frequency and very high frequency are kind of off the scale here. So just looking at this 8 hours of data, you might not if these weren't labeled, you might not pick out any marsquakes, but this is what they look like in spectrograms like this. These are basically candidate events, and there's two on here. There's a low frequency event, that's this, and there's a 2.4 hertz event, 2.4 hertz event, that's this. Yes.
Maybe this is just the projector, but at the top right, it kind of looks like there's a sweeping signal.
This.
No, above it.
This.
Yeah,
Oh,
is that just a projector thing or is that real?
that looks like there is. So that would be some sort of dispersive signal.
Uh-huh.
It's not unheard of to have these types of kind of sweeping frequencies that are usually related to the lander. So sometimes lander activity can produce kind of like dispersive signals. Whether like it's like I don't know if this is an example of that, but that has been cataloged. Like if the lander's moving its boom arm or something, it can cause these types of transient signals that show up as kind of like dispersive. This is like not a chirp. This is like kind of like an inverse chirp. Okay, so just statistics. Let's look at them for a second. If we break it down by event type, the vast majority are in the high frequency family, and far fewer, less than 100, are in the low frequency family. We also categorize them by quality. That's based on signal to noise ratio. So A being the highest quality, D being the lowest. For the rest of this talk, it's really these ones I'm going to be talking about, the broadband and low frequency marsquakes. And that's because these look most similar to tectonic earthquakes, and we can do the most science with them, particularly the high quality A and B events. So there's not a whole lot of them that were detected, but we can get a lot from them. Yes.
How would this compare on like the Richter scale? Is this something we would feel if we were walking?
Some of them, yes. Actually, okay, so just real quick. There was an earthquake south of Decatur the other day, and everyone know about this. Anyone feel it? That was a magnitude 3.8 on the moment magnitude scale, or local magnitude scale. So a lot of times we don't use specifically Richter, but it's very similar. 3.8, it happened a couple 100 kilometers from here. Most of us didn't feel it. I think some people reported on USGS that they did feel it in Champaign. 3.8 on Earth, no big deal. 3.8 on Mars, very exciting if you're a planetary seismologist. That's kind of the upper end of some of these events. We're on like the 3.8 into the 4s. So they're small by Earth standards. Very exciting if you're a Martian seismologist. Okay, so we can also think about where these things plot. It's difficult to locate marsquakes with a single seismometer, but there are ways of doing it. A lot of the most interesting marsquakes that we'll talk about, the broadband, low frequency, high quality events, map almost due east of InSight in this area called Cerberus Fossae. Again, this is this sort of tectonic feature that I'll talk more about. Yeah.
Do these events have different modes, like horizontal or vertical modes?
Of vibration, yes. Yeah, so there's different phases that are detected. In most events, we only see P and S, but there are also other phases sometimes that we see. So we'll see surface waves sometimes, Rayleigh and Love. It's a 3-component sensor, so yeah, you can pick apart the different types of particle motions. Yeah, so that's a good point in terms of how you locate these things. A lot of it has to do with the polarization of the body waves. You can think of like if I equate it a lot to locating like thunder or a lightning strike if you heard it, right? So you can count if you saw lightning and you look the time difference between the thunderclap and the time you saw it, that gives you a distance. The direction, if you didn't actually see the lightning and you didn't know what direction it is, you can still pick out what direction it probably came from because your ears are sensitive. There'd be a delay between when one ear heard it and the other ear heard it. So it's sort of like that, but we don't have 2 ears on Mars. We only have 1. So we rely on particle motion. So the P waves are polarized in the direction of propagation. And so you basically get a vector of the incoming energy direction. And so you can kind of point back at the source. So you get distance from the time difference between P and S, and you get the direction from this polarization angle. Yeah.
When you did the conversion to like a 3.8 earthquake on Earth, Are earthquakes on Mars? I don't know how that scale is exactly calibrated, but
Mhm.
would you feel it more on Mars if there was the same amount of energy as an earthquake?
So that's a good question. Yeah. Um, there's a lot of things that control local ground shaking.
Mhm.
So a 3.8, even a 3.8, like it depends on what the local geology is. If you're in a sedimentary basin, even on Earth, you might feel that stronger because there's basin amplification effects. So it depends on the substrate you're on. On Mars, yes, you might feel a little bit stronger because the intrinsic attenuation might be lower, meaning that waves can propagate farther without losing energy. So yeah, there's a lot of at play, but it depends kind of on local side effects and also kind of the crustal properties in bulk. That's also a good question. If we look globally at where all the high quality marsquakes map, you'd see this. This inset here, again, this is the Cerberus Fossae region. The fossae are fissures, and they plot as these red lines. Okay, so a lot of these cluster right around these fissure systems, but there are some other ones that are farther away. The reason we have these kind of big boomerang looking regions is that's the uncertainty bounds of the location. So there's uncertainty in both distance and the azimuth or the direction to the marsquake. So it kind of traces out these big bananas. This actually is an old picture because 1000A turns out to be an impact that has a known crater. So we know precisely where this one is, but I'm getting ahead of myself. All right, so let's talk about what's causing marsquakes. And before I do that, I want to talk about what causes earthquakes. This is a map of the global distribution of seismicity, and it really lights up the plate boundaries. That's what you see as the sort of first order takeaways. You see the tectonic plate boundaries. But that being said, you also see some earthquakes that are happening in plate interiors. You know, we just had one again. We had one in Illinois. That's not a plate boundary. But about more than 95% of earthquakes happen at plate boundaries. And so what's causing those earthquakes? It depends on the tectonic setting. And so really, if we think about what an earthquake is in general, it's caused by slip on fault planes. So a lot of things can produce seismic waves, things like impacts, explosions, but most earthquakes are caused by slip on fault planes. And you can think of kind of an earthquake cycle where stresses kind of build up on faults, and then during slip, the seismic energy that is accumulated is released as seismic waves. And so that's what we feel as ground shaking. And so faults are just basically planar fractures in the rock. They can develop as the crust undergoes deformation, the tectonic deformation. And then the movement that happens during an earthquake is when there's slip on either side of a fault plane. There are different styles of faulting, and that relates to the sort of deformational regime, whether it's extensional, compressional, or sort of in the middle. All right. So different tectonic settings on Earth relate to sort of different plate motion behavior. So real quick, this plot up here is showing the global strain rate map of the Earth constrained by geodesy. So mostly from GPS. And you can see that, so the brighter the colors, so the more red, it's higher strain rate. So faster deformation is taking place. And almost all the deformation is concentrated along the plate boundaries where we see earthquakes. This figure is now showing, instead of just the magnitude of the strain rate, it's actually showing the type of strain. So blue would be where you have compressional strain, red is where it's extensional, and green is where it's sort of in between. And that corresponds to different faulting that we would expect to see. So where it's compressional, we would expect to see what we call reverse faulting. Where it's extensional, we'd expect to see normal faulting, basically things being pulled apart. And where it's sort of in between is where we expect to have transform faulting or strike slip faulting, where blocks are kind of sliding horizontally past one another. That's like what we see in San Andreas. Okay. So seismologists have a way of representing these different types of earthquake mechanisms. We often refer to them as beach ball diagrams or focal mechanisms. And without telling you too much detail, I'm just going to show you what they look like. So this type of faulting, a reverse fault, looks kind of like an eyeball with a shaded center. a strike slip fault. It looks like this, where you can see all four quadrants of the beach ball, and then a normal fault looks like the reverse of a reverse fault. Okay, and what these things are actually showing us are the focal mechanism parameters, sort of the fault plane geometry and sense of slip. All right, and that can be described by three different parameters: a strike, a dip, and a rake. The strike of a fault is the compass direction that the fault trends in. So if we think about this plane here that intersects this block is the fault, the strike would be this direction from 0 to 360, which 0 is north. The dip is how steeply the fault plane dips from the horizontal. So it's this angle. And the rake is the direction of slip within the fault plane. So if it's positive, it's compressional. If it's negative, it's extensional. All right. So that's what those beach balls are showing. And so if we look at a picture of the global seismicity, the focal mechanisms of Earth, this tells us a lot about how our planet behaves. This is basically if you had one picture that would summarize kind of tectonically how the Earth is working, it's a picture like this. And so you can see, for example, if you look here in South America, you can see all these reverse fault or thrust fault mechanisms, and that's because we have convergent behavior between the Nazca plate subducting under the South American plate. You also see that up in the Alaska Aleutians where there's subduction happening. I'll take another example here in East Africa. We know there's active rifting going on, so things are being pulled apart, and you see all these normal faulting mechanisms. Yep.
So in one of your previous slides, you showed that there were like 3 basis beach balls.
Yes.
Do those come together to make like composite slips, and that's why they look different on this plot?
Yes, that's a very good point. So those are kind of those are like the really simple views of the 3 different types of focal mechanisms. But you can have combinations. You can have like oblique slip, and so any orientation. You should really think of the beach ball as like a 3D sort of focal sphere. And you, depending on what angle you look at it from, you can actually see kind of any of these intermediate behaviors. So yeah, you can have more complex sort of types. You also see this one is a pure normal fault, but it's not oriented north-south. And so the trend of the curved planes actually tells you the direction of the fault. All right. So I could spend a lot of time talking about beach balls, but it's something that like takes an entire lecture to really kind of grasp. But what I'm working on with my group is trying to come up with a picture like this, but of Mars, which would tell us a lot about sort of the tectonic behavior of the planet. All right. What types of marsquake sources might we expect? Prior to the InSight mission, one hypothesized source of seismic activity was basically thrust faulting due to planetary contraction. So thermal cooling and shortening of the crust would lead to something like this. That's been known to happen on Mercury, and possibly could explain some of the seismic budget of Mars. But other things have been suggested related to, for example, extension or magmatic processes. And so a big question I'm interested in is, can InSight distinguish between these types of mechanisms, and what are they telling us about the tectonic behavior? Yeah.
So in the beginning of your presentation, you talked about how it's a single plate, on the outer shell of Mars. So how, like, there are no multiple tectonic plates to even give rise to this activity. So
So that's a really good question. And I think the best kind of analog to think about is a setting like central Illinois, where there are fractures in the subsurface, and in the subsurface, the crust, here in Illinois is under stress. Okay. And so these fracture systems that could be ancient faults are being loaded by stress. And occasionally, even though it's not a plate boundary fault, these smaller faults can produce slip and seismic activity. So it's not a fault system that kind of breaks the entire lithosphere and causes large scale motion between different plates, but there can be fault systems within plates that accommodate smaller amounts of motion. Okay.
Also, Brian feels so much.
Okay.
To follow up on that question. So in both cases, for Illinois and Mars, is the underlying source of the stress motions in the magma?
Okay. So.
Or mantle, I meant to say.
Yeah. So I assume you meant mantle. In some cases, so yeah, there's different, in the case of Earth, the primary forces that are responsible for plate tectonics and earthquakes are what we call slab pull. That's basically the downward pulling force of the heavy oceanic plates as they subduct. And then ridge push, which is at mid-ocean ridges, we have plates that are spreading apart. But there also can be what are called basal tractions, and that's more like what you're talking about, where it's the sort of convective flow beneath the lithosphere that's imparting stresses in the crust. And so there's no simple answer about how you kind of deconvolve all of those. But at least in the case of Illinois, it probably has to do with sort of stress transmitted from plate boundary processes. But it's a good question, and it's actually maybe more of a complicated question than I can give a good answer to right now.
Fair enough. Thank you.
Yeah, were there other questions?
That answered it.
Okay, cool. All right, so let's talk about what some of these events were. First of all, I'm going to talk about this event called S235b. It's the 235th Sol, and the second event that was recorded on that day. This was the first marsquake that got everyone really excited. And it's because it looked a lot like an earthquake. We saw really clear P waves at longer periods. Here's an S wave. This is vertical north and east motion. This is timed in seconds. And it was a magnitude 3.7. Again, smaller than the Caper, but it led to these beautiful waveforms. And so this high signal to noise ratio allowed accurate location and also the first marsquake focal mechanism determination. It was documented in Brinkman et al. in 2021. And how you do this with a single station is you basically estimate or you minimize the misfit, this chi-squared misfit, between the observed body wave waveforms, that's either P or S, and synthetic waveforms that you model assuming a given structure of Mars. So you can do this in various different ways. There's lots of different ways to do inversions, but with this type, there's few parameters. So it's really strike, dip, and rake that you're varying, and then event depth. So you loop over all of these, you propose a given focal mechanism, you synthesize data for that, and you compare it to the observations, and you minimize that sort of globally. And so these are some of the first focal mechanisms. So the observations are in black. Blue are from sort of a suite of decent fitting results. And so this is basically P and S wave fitting. They don't look perfect, but also I want to emphasize that they're actually only trying to fit in this gray area. So does anyone remember what kind of fault this is? It's a normal fault. So this is extension. And the sources are in the mid crust, somewhere between about 17 and 32 kilometers. So what is that telling us? It's basically telling us that the Cerberus Fossae region, where here's 235b, that this is undergoing extension, which is sort of consistent with preconceived notions about what's going on here. If you look at later studies, here's one by Jacob et al. In 2020. You can see other marsquakes, especially if you look at these ones. They all, most of them show this sort of normal faulting mechanism, striking in roughly the same orientation as these fossae. So basically, the takeaway from this is that a lot of the seismic activity on Mars is coming from this active rift system with north-south extension. And some of the active tectonics and recent volcanism kind of indicates that the active seismicity we see today may be related to magmatic processes such as dike injection or magmatic intrusions that are accommodating this extensional offset. So here's some of these at depth. Here's some of these beach falls that show kind of how it would relate to this kind of magmatic intrusion at depth. So no volcanic eruptions, but basically magmatically accommodated extension. This is what the Cerberus Fossae actually look like. I mean, they're pretty striking features. You can see here's these Fossae systems, these big fissures. They're surrounded by volcanic plains that are as young as 10 million years. Now, remember, I said everything else. A lot of the other features we see on Mars are as old as 3 billion or older. 3 billion years or older. So these are very young, geologically speaking. And there's active tectonism going on here. This is not oriented well, this direction is north, so sort of, it's like north-south extension. Okay. If you want to get really arm wavy about this, there is a paper in Nature Astronomy that suggested the fossae, that's these systems, or these fissures, are being driven by active upwelling, whole-scale mantle upwelling we call mantle plume. Okay, so this is, there's evidence both from the seismology, but also looking at the gravity and geoid signature that there's some sense that there may be large-scale upwelling of the mantle. All right, so what am I doing on time? Yep.
15.
15.
So is that similar to what would have happened with the Tharsis bulge, but maybe much earlier?
Absolutely, that's one of the main hypotheses about Tharsis, and even the development of the sort of dichotomy boundary, where you have the young volcanic plains in the north and the older highlands in the south. One of the ideas is that you had what we call degree 1 convection, where we had basically one hemisphere was upwelling and one hemisphere was downwelling, and it could have left this long-term imprint on the planet that we still see. But mantle plumes are thought to exist and be responsible for hotspot volcanism on Earth as well, in places like Hawaii. So it's perhaps reasonable to think they might exist other places. On the marsquake side of things, the last thing I want to talk about is one of my favorite marsquakes, which is S1222A. This is the largest marsquake observed by InSight. The initial estimate was a magnitude 4.6, but I think it's a little bit smaller than that. It's not a Cerberus event. It was actually here's Cerberus, here's InSight, and here's where this one plots. It's a little bit north of the dichotomy boundary, but it actually kind of straddles it if you incorporate uncertainty. This is the only tectonic marsquake that recorded clear surface waves, both Rayleigh and Love waves. So it's very exciting. What was the mechanism of this marsquake? That's what I tried to address in this paper in 2023. And it turns out that it's likely thrust faulting. So the opposite sort of case as the last one. Here's the waveform fitting. Again, this is showing P, S. Now I can actually do Rayleigh and Love fitting. The observations are in black. The red are the predicted seismograms for this beach ball. And it likely is a thrust fault in the crust at about 20 kilometers depth. The orientation of the fault aligns with mapped contractional features from geomorphology, basically wrinkle ridge features. So it's plausible that this is representing reactivation of buried faults that are responsible for some of these wrinkle ridge in these wrinkle ridges in Avernus Dorsa. And I would argue that this is the clearest evidence or the strongest evidence that some active tectonics on Mars is being driven by planetary cooling and contraction. All right, a different type of source now. I mentioned meteorite impacts. We were very fortunate that during the mission, 2 sizable meteorite impacts were detected, and that's 1094B and 1000A. And so you can see the paths of InSight as these lines. You can see the arc distances in degrees. Both events contain Rayleigh waves, which turned out to be very useful. Orbital imaging from CTX and MARCI confirmed that these events that were detected by the seismometer were linked to new craters that we see from the camera, from the images. A lot of exciting stuff was done with this. This is a close-up of the impact crater. You can see this ejecta blanket, it's dark material. Here's a high-rise image of the crater. It's about 150 meters in diameter. So bigger than a football field. It equated to about a magnitude 4 earthquake. And these blocks of light-colored material, anyone want to hazard a guess at what that is? Those are boulder-sized blocks of water ice that were excavated from the near subsurface. And so that was very exciting. It's close to the farthest south, the closest to the equator that this type of sort of ice has been extracted from a crater like this. Yeah.
Is the ice still there?
That's a good question. I'm assuming it's sublimating quite fast, but I don't know. That's something I'd like to follow up on, but I think it's probably, I don't know, but it's probably not going to be there long if it's still there. Yeah.
Brian has a question online.
Okay, sure.
Yeah, so how deep did it go? And does Mars get whacked more than us because it's closer to the asteroid belt?
Does Mars get back? Okay, first of all, the depth, it's the depth is comparable to the width. So it's you know, it's on the order of 100 meters or so. Okay. Does Mars get whacked more than us because it's closer to asteroid belt? That I don't know. There's a lot of, I mean, it also doesn't have an atmosphere that protects it. So I don't, you know, if you're looking, well, it has an atmosphere, but it doesn't, you know, serve as a filter as efficiently as ours. The impact rate is something that both InSight and the people who run HiRISE and CTX are trying to constrain on Mars. And I think there's some uncertainty of the actual impact rate on Mars, like the present day impact rate. So I don't know enough about it to say one way or the other how many actual impacts are reaching the surface. I'd imagine it's more on Mars, but primarily to the atmospheric effect.
Yeah, got it. Cool. Thanks.
Yeah. Okay. So a lot of people are excited about looking at the crater. As a seismologist, I was more excited about the waves that these impacts produce. And one of the things that you can do is you can actually look at the Rayleigh waves and the travel times from the source to the receiver to constrain the crustal velocities. And so that's what we did in this paper in 2022 for these two impact events. We used what we call the dispersion of the Rayleigh waves. That's the frequency dependence of the travel time to constrain the crustal shear velocity. That's the speed at which S waves travel. And so these are the inversion results. This is VS in kilometers per second, and this is depth. Remember the thickness of the crust is 50 kilometers or so. And so we're really constraining the velocity profile and sort of the mid crust down maybe to the uppermost mantle. And what we see is that the velocities are about 3.2 kilometers per second, which may not mean much to you at first, but it actually tells us a lot about the material properties along the path averaged crustal structure. Okay, so the takeaway here is the seismic velocities are lower than what we would expect if this is sort of unbroken volcanic rock. Like if it was pristine basaltic rock, the velocities would be higher. And so what you need to explain these relatively low velocities extending through the crust is a lot of porosity. So you need fracture systems that extend very deep into the crust, potentially tens of kilometers. So that's one way of looking at sort of path average velocity structure. If we want to look directly below the lander, there's a different technique we can use, and that's called the receiver function technique. And I'll briefly try to explain it with these cartoons. So this is showing a seismic wave. This is InSight. This is a seismic wave front arriving below the station from a distant marsquake. And so the P wave is basically going to be the first thing to arrive at that station, and the motion is going to be like this. And so when this wave hits this station, it's going to produce a wiggle. But as the P wave interacts with layering below the station, so whether it's the crust mantle boundary or other types of layers with varying material properties, some of the P wave is going to convert to S. And we can look at these secondary or daughter S waves and isolate them from the P wave. So now on this trace, this is what we would call a receiver function. These PDS phases where D is the depth of a conversion, tell us about the sequence of sort of layering below the station. And so we can sort of invert that to come up with the kind of a layer cake structure below the lander, so locally to InSight. And so the first time this was done was in 2021 by Maguire Endrun et al. And the results look something like this. There's 3 distinct pulses, which correspond to 3 distinct layers below InSight. And it looks, and if you invert those data, you get something like this. So slow layer, slightly faster layer, and then there's actually another layer down here. So the crustal, so it's sort of 3-layer crust conversions at each one of these layers. And so this is showing a histogram of the likelihood that there's a discontinuity at each depth. So 3-layer crust, with a total thickness of around 42 kilometers. And there's these extra intracrustal discontinuities. This has been used to argue, this is a very sort of contentious argument, but the low velocities constrained by receiver functions below InSight have been used to argue that there needs to be present day liquid water storage below the lander. And so this is a complicated figure, but the takeaway is they use that Wright et al. Use mineral physics modeling to basically try to match the seismically constrained VP, VS, and density by predicting what the wave speeds would be for different lithologies or rock types, porosities, and then liquid water fraction. And they found that to explain these very low observed velocities, you would need some amount of water. And so this is a quote from their paper: a mid-crust composed of fractured igneous rocks saturated with liquid water best explains existing data. This made like CNN headline news. My dad called me and asked me if I had heard about this study. And so it got a lot of attention. It's very, there's a lot of pushback on it too, because a lot of people have also shown that you might not need liquid water and the water could be stored in other mineral phases. So this is, take it with a grain of salt, but it's hard to rule it out entirely, but it's potentially very exciting. Another thing we can do with these imaging techniques is constrain the global crustal thickness and its variation. So if you take seismic observations and combine them with gravity, we can come up with maps like this. So this is crustal thickness. The southern highlands have thick crust, the northern lowlands have thin crust. On average, the crust is between about 42 and 56 kilometers thick. If you put that in context of comparative planetology, it's actually on the higher end of the spectrum. So it's thicker than the lunar crust and thicker than our crust here. Last topic. So I did promise I would talk about the core. So as shown in this simulation, the core, which is this black region, is a very good reflector of seismic energy. In fact, if it's a liquid iron core, and this is an S wave that's propagating down, it's actually a perfect mirror because the S wave won't propagate through the liquid. So it will reflect all of the energy back up. And so core reflected phases, particularly SCS, where the little c indicates it reflected off the top side of the core, are routinely observed on Earth. And they were one of the sort of things we were looking for with marsquake data. And it turned out that finding these faint core reflections was a bit of a fishing expedition and took a lot of careful work. But we did end up finding convincing evidence of SCS from marsquakes, from about 11 different marsquakes. We do a lot of kind of careful processing techniques, including stacking data to enhance signal to noise ratio. But the takeaway is shown in this picture, where the recorded SCS, here's these S waves bouncing off the core, constrained a core radius to 1,830 kilometers, plus or minus about 40 kilometers. And the amplitudes of the SCS phase really constrained that it had to be a solid liquid interface. Okay, so this was published in Science in 2021. Again, got a lot of attention. It's been cited hundreds of times now. Yep.
What do you mean by a solid liquid interface?
So meaning that the mantle is solid, it's solid rock, so S waves can propagate through it, and then it's reflecting off a liquid outer core. Okay, so it's just I think there's there's a tendency, I think, when we talk about planetary scale stuff like this, to think that a lot of this stuff in between the core and the crust is liquid also, but on the Earth and Mars, it's solid rock by and large, with some regions where it's molten. Okay, so this, like I said, this paper's been cited a couple hundred times, but this is, I think, over 300 times now. It's maybe an example of how fast science can move, because this was published in 2021, and well, this is just showing here's SCS here. This was published in 2021, and this was the picture of Mars, revised by Insight. 2 years later, 2 papers came out in Nature that basically said, hey, not so fast. Those SCS waves that you think you saw are probably not actually reflecting from the core. And so what they basically argued is that seismic phases that traverse deep into the mantle, that basically graze the core, showed that this model, the sort of large core model, was not compatible with those observations. And in fact, what you needed, the way that you could make all the data consistent is if the core is smaller, but enveloped in a layer of molten silicate liquid, basically magma at the base of the mantle. Okay. And so in this case, the true core radius is about 1650, 1675 kilometers. This actually made a lot of geochemists happy because this model of the planet, the core is so large that you had to have some sort of exotic compositions to really explain the integrated mass constraints of the planet. If you make it's an iron core, if you make it too big, you have to start incorporating more and more light elements to satisfy the mass of the planet and the gravity. So you needed a lot of light elements for this to make sense. And this is sort of more compatible with what we know about the geochemistry of Mars. Here's a quote from this opinion piece from Nature. Having molten rock right up against molten iron appears to be unique. So, and this is actually telling us something about the thermal evolution of Mars, particularly that to generate this basal magma ocean, there needed to be early segregation of the mantle and basically sequestration of heat-producing elements near the core. And so that's kind of a new discovery. So I'll just leave the conclusions up here and then go really, really fast. Mars is a tectonically active planet. That was science goal too, we know that. The most seismically active area that we can see with our one seismometer is Cerberus Fossae, which is undergoing extension, possibly related to magmatic activity. Thrust faulting does happen on Mars, and it likely indicates crustal shortening and planetary cooling. The crust of Mars is about 50 kilometers, and the presence of groundwater storage in the mid-crust is possible. I put that as a big question mark. And some of the work I'm doing is trying to address that question. And then lastly, the Martian core is likely about 1650 to 1675 kilometers in radius and has this liquid outer layer. Okay, thanks.